So, how do attackers impact an OT or an ICS environment to where we have an availability issue, where we bring down a plant, whether it's causing a blackout, right? Or what if we shut down a manufacturing line and we're no longer producing that specific product? What would the impact be? Or what if, right, worst case scenario is always we talk about is an explosion, right? Would be very rare to happen. And it's always considered that worst case scenario, but it is one we have to consider, even though we also want to focus primarily on those types of attacks and scenarios that are most commonly likely to happen. Of course, we're looking at this from the perspective of a pen tester, thinking like an attacker and how we do these things, but also identifying gaps in the security program for that OT environment that we can help our clients address. That's what we're going to talk about in this module. So, yes, this section is where we move away from discovery and collection. This is where we start talking about having an impact in the environment. And that's what we're actually going to start with when we talk in this section about not just execution and privilege escalation, but we're going to talk about those impacts that an attacker or potentially a pen tester could have in an environment. Of course, from a pen testing perspective, we're looking at this from a testing perspective. But when we think about this from, again, the attacker perspective, and ultimately what we're trying to do through pen testing is helping an OT or an ICS environment become more secure. So, what are we trying to make them more secure from? So, when we look at, what can happen in an OT environment from an attack, so we can talk about, yes, we usually think of things like worst case scenarios, like an explosion. And that's where we can talk about, yes, damage to property. When we start thinking about, well, what other types of an impacts can an attacker have? So some that we focus on are things like denial of control, right? Preventing an operator from being able to take action when it's required. What if there's a runaway process that you need to stop before that there is some type, let's say an explosion, which again is worst case, or just simply maybe the manufacturing line shuts down. Denial of view. This is where, what if the operators can't see what's going on in the environment? I always go back to, thinking of Stuxnet, where you're that operator sitting in the control room and you're watching all the lights for these centrifuges and everything looks perfectly fine, even though behind the scenes or those centrifuges were physically breaking down because of Stuxnet. Of course, when we start talking about loss of availability or operational availability, right? It wasn't just a few months ago we had the Jaguar Land Rover outage where they lost all manufacturing capabilities globally for 5 months before they started to come back online. And loss of control, same thing, kind of similar with denial of control, right? Preventing the operators from being able to make changes. Think of, go to an HMI. Even maybe the HMI is available, but what if the HMI is lying to us? Or what if I can't log in all of a sudden to the HMI if it requires credentials? There's a lot of different ways we're going to look at how can we prevent operators, right, from being able to control the process and the environment. Of course, important to the business, we start talking about, sure, loss of productivity, just like we see in the IT world when things shut down, but also lost revenue, right? That Jaguar Land Rover incident, which in that case, the attackers weren't even in OT. They just shut down the IT environment and all of the systems in IT that the global manufacturing lines required to run. And it cost the company over, and this is the starting number, $2 billion and counting. So from the business perspective, and that's where I get concerned, right? It's not just that somebody can't go buy a brand new Jaguar or a Land Rover, but it's over 200,000 people that were at risk of losing their jobs. Most small, medium size, let's say like manufacturers, when they go down, if they go down for 5 weeks, they shut their doors in 3 to 6 months. They go bankrupt. And then all of those people that work there, they have no jobs. Their families have no paychecks. Of course, some of the more serious concerns that we have in OT from a cybersecurity perspective all revolve around safety. So if we can't protect the people on site or that live in the vicinity of that plant, what if we can't keep the plant itself safe, really keeping it safe from itself? If an attacker can come in and manipulate the environment to cause some type of situation to do damage to the plant. Talk about manipulation of control. That's where some of the more interesting, of course, conversations and examples we get into is where we can interact. We can inject ourselves into the control and monitoring mechanisms for a process. And we can change the process to have that impact. So how can we manipulate control? How can we manipulate what the operators are seeing also when we talk about manipulation of view? And then there's always that idea of, sure, theft of operational information. So, of course, typically the number one concern in IT environments is always preventing theft of proprietary or confidential information. And that could come into play in OT environments. Some OT environments, if an attacker got in and reverse engineered their process, and they might not necessarily be concerned with that, while others are. They would consider that sensitive information. So these are the more common types of impacts that we would see as a result of an attack against OT and or the IT networks that they're connected to. These are, of course, the types of impacts we're trying to prevent. These are the types of impact that we're trying to highlight for the clients by doing the testing. So we can show them that the gaps that they have in their current architecture, their current cybersecurity program, right, the gaps that they have that they need to address to lower the chance, right, the probability of any of these impacts happening. So when we go back to the OT penetration testing methodology, remember the very end is where we have that impact. Now we've already talked about reconnaissance, right? Finding our ways into the OT environment, right? Gaining that initial foothold, the initial access. Then the last two videos, we talked about discovery and collection, right? Finding the different assets on the OT network, mapping out how those assets are related, trying to reverse engineer how we monitor and control the actual process and the environment. What is that process? How are these different assets programmed? How do they control this equipment in the real world to do what they do? And then ultimately, it's about having that impact, whether it's right that extreme example of an explosion, or more commonly, just shutting down a manufacturing line, or maybe spoiling a batch of pharmaceuticals that we're manufacturing. It's all about eventually getting to and preventing that impact. That's why we're doing the penetration testing in the first place. So now we're talking about exploitation. Remember, we're moving from discovery and collection into exploitation. Now, there's a lot involved in exploitation. So when we look at exploitation, this is what we're going to talk about. We're going to talk about execution, then move into privilege escalation. So what if I gain access to an asset, but maybe it's limited? I don't have administrator or full control, right, or root level access, and I want to gain complete control over that asset. That's where we use privilege escalation attacks. Lateral movement, as we move from system to system within the environment. Pretty typical or fairly straightforward if we're talking about Windows machines. We'll talk about also how does this look on OT assets like PLCs and HMIs. And then we get into the interesting parts, right? The last two phases right before impact. And so we'll talk about these in next videos, talking about inhibit response function and impair process control. It's where how we can prevent operators from taking action that would be required before something bad happens to ultimately, again, have an impact in the environment. So let's talk about exploitation. So we do have exploitation broken into two parts. So we talk about execution and privilege escalation. So when we think of execution, we're usually talking about gaining access, at least some level of control of an asset or a system. And we're going to start to see how easy this can be using assets like PLCs in the OT environments. And we've already started to actually see this in the course. Remember, with PLCs that run unauthenticated OT protocols like Modbus, right? That's a level of access, right? I can actually read everything in memory on that system, and I can make changes to anything in memory on that system to have an impact in the real world. That's a level of access to the system. Now, some systems, again, we might have very limited access that we want to then take that initial foothold on that asset and then gain full, complete control over that asset. So we're going to talk about that as well. So when we talk about, again, execution or privilege escalation, and here's an example. We talk about, let's say, as a pen tester, we're in let's say, a test environment, and we find an HMI, and that HMI is running on Windows. So remember that HMI, in this case, running on Windows as a web service, right? It inherits all of the kind of vulnerabilities that we have in the IT world from that Windows perspective. Because we have to remember that HMI running as a web interface, well, that web app has vulnerabilities. And it's running on a web service, and that web service has vulnerabilities. And that web service runs on an operating system, and that operating system has vulnerabilities. So in this case, we gain access to the HMI, right? Because we found that the web app itself that's displaying the HMI has a vulnerability. So we take advantage of that vulnerability in the web app to gain access to the Windows operating system of the HMI. In this case, we gain access to the system in the context of the user account that the web app is running. So when you install a web app on a Windows system, right, you're going to associate it with account. Now, by default, right, that can often be system. System has full control over the system itself, right? The system account that represents essentially the kernel of the Windows operating system. So system, the account, actually has even greater permissions than the administrator account, believe it or not. But in this case, we gain access to the operating system using a vulnerability in the web application. So in that case, we gain access, but it's limited access. But while we're on the machine, and this is one of my favorite types of vulnerabilities to work with when you're on a Windows system. Well, what if we get that initial foothold and it's limited, but I want to become a full administrator. I want to gain system level access. One of the things we'll do is we'll see what else is running on the machine. And it's very common where you can find another service running on that machine with system privileges. And sometimes, not always, but sometimes, the executable for that service actually has writable permissions. So you can actually replace that executable with whatever you want. And even if it's one where, oh yeah, we build in a reverse shell, we restart the service or we restart the system. And when that new service comes online, it establishes a reverse shell. Remember, that reverse shell is a connection from that compromised host, in this case the HMI, back to a machine that I control. And you actually are going to go through this in the labs. We're going to establish that reverse shell from the compromised system back to a machine that I control. And it gives me access to the operating system level, in this case, as if I was sitting there at the command line and I'm able to type and issue commands. So when we talk about execution, you see, we're going to focus on these different 5 techniques that we see on MITRE ATT&CK. Of course, I mentioned previously, I warned you, we're going to talk about operating modes or operational modes. We're going to talk about how you can make changes through APIs. We see APIs pretty much everywhere in OT, just like we do in IT. Maybe not as much, but they're definitely there. About making changes through a GUI like the HMI. How we can make changes to controllers and how controllers like PLCs go through their process to be able to, well, remember, monitor and control the process and the environment. And then we'll talk about how we can create and use different web shells as well to manipulate different types of systems in the environment. And so these are probably some of the more common techniques that we see used in the environment from an execution standpoint. So remember, as a brief reminder, remember when we have a controller like a PLC, right? The PLC, when it's up and running and it's doing its thing, we consider that right? It's going to be in run mode. We should have that key switch we've talked about placed in run mode. So we can't have remote parties at least change the version of firmware remotely on the controller for us. But when you think about, well, if I'm an attacker in the environment and I want to have an impact, there's a couple of ways I can do that by manipulating the operating mode of, let's say, a PLC. Because what if I can take a running PLC and just stop it? And what if I can stop it at a specific point in the process to have the most damaging impact? So if I can take a PLC and remotely take it from run to stop. And now no longer do we have this computer, right, sitting there and controlling the process. The process is often running on its own. Or what if I have the ability to take a PLC from run mode and put it in program mode? So I can put a different version of firmware on the PLC. Maybe that has a malicious component to it. So it is important. A lot of people kind of blow off the operating or operational mode of controllers. But that's why it's important to watch all of your controllers and your PLCs to make sure that they're in run mode. And if you ever see them come out of run mode, you investigate right away to see what's actually happening. So we're going to look at some different ways on how we can remotely determine what operating mode a controller is in, right? Whether that's accessing the memory in the controller to see if we can find a tag or data there that will tell us what mode it's in, or maybe we actually have other options as well. Besides, walking through a facility and seeing, oh, there's a PLC and I can see that it has a physical key switch and the key switch is in remote program mode, which is not what we want to see from a cybersecurity perspective, right? We want it in run mode, which is going to be the most secure mode for those controllers. So we're going to look at not only how we can determine remotely what run mode or what operating mode those controllers are in, but how can we make a change remotely. So how can I take it from run to remote program or to stop? So there's different options that we're going to look at. So a lot of controllers, they have a hardware switch, like with the key switch, or sometimes it's a little dip switch on the kind of the lower end models. I guess the true lower end models don't have any type of hardware switch. But you have hardware switches, of course, that requires physical access to see, to be able to interact with. Now, you can do it through the programming software. Remember, programming software is dependent on what vendor you're using. So if I'm going to try to, let's say, take a Siemens PLC from run mode to remote program mode, I have to use the Siemens software to do that. So we have to have access to the Siemens software. And then is that Siemens software going to ask you for things like usernames and passwords? So you have to be prepared to, what if you are actually asked for credentials? Of course, to get there, you probably had to get on a system that also required things like credentials. And we can also think of the HMI, right? The HMI that controls and interacts with that PLC. Right? It has the ability to make changes to the PLC. So we can look at hardware switches. We can use the official programming software from the vendor. Even an HMI we can use to interact with that PLC and determine, is it in a certain, what operational mode or operating mode is it in, and then potentially use that route also to take it out of run mode. So we just started to briefly talk about this earlier in the course, but talking about the PLC scan lifecycle. So where we talk about, and the first thing that the PLC does is it brings in data. Right? It brings in the information from the sensors that we have in the environment to monitor, right? To understand what's going on in the environment, right? What's the pressure in this tank? Is this motor on? How much fluid is passing through this pipe at this one point in time? We have to bring in all of that data that we're using to monitor the environment. Then the PLC actually runs its scan, its logic. Say, okay, based off of this data, we determine, do we need to make changes in the environment or not? Remember our thermostat example earlier in the course. Right? This is where the PLC, right, it has the temperature data, right? It just brought that in through the input scan. So it knows that the room is 75 degrees and it knows the set point. The desired temperature is 72. So based off of the programming in the PLC, based off of that logic, it knows, you need to have the air conditioner on. And so with the air conditioners not on right now, when we get to the output scan, this is where the PLC takes any action that it needs to based off of its logic, and it'll send out the commands, the signals, in this case to the air conditioning unit to turn on. And then we get to housekeeping, or kind of try to tie up a few loose ends and make sure everything is working appropriately. And we're going to talk about that a little bit more in detail. But there's a reason that there are 3 different techniques related to the operational mode or the operating mode on controllers. There's 3 of those different techniques listed in MITRE ATT&CK. Because attackers, not only once they're in the environment, they want to find out what operating mode that PLC is in. But then they also want to have the ability to change that operating mode. And why? So we have, in different cases, right? We mentioned we could potentially bypass different safety or control logic that's programmed into that controller. Now, that's usually going to be done by uploading malicious firmware or logic to the PLC, or I should say downloading in the OT. So we're going to put malicious firmware or logic onto that controller. And talk about Oh, if I gain access to that controller, right, that gives me direct control over the associated process, right? Whatever we're monitoring and controlling out in the real world. We're also going to look at, and this is more for the next video where we start talking about how do we disable alarm mechanisms. So if I'm an operator in an environment and an attacker is making changes to a process, by default, right, if those changes are going to cause some type of condition where there's going to be damage to the plant, right? There's safety issues or there's going to be a failure to the process that we need to step in, right? We're going to want to get the operator's attention so they can step in and make changes to prevent the bad thing from happening. So we should have, bells and whistles and blaring klaxons going off. We should have screens flashing red, right, to get the operator's attention. Well, what if we disable those? So the PLC knows all these bad things are happening and it's trying to get the attention of the operators, but what if we silence those alarms? So there are no flashing red screens and there's no blaring sirens going off, right? Loss of visibility. And in a way, it's a loss of control, right? Because the operator needs to take action, but they're not because they don't know they need to. Now, you can cause confusion among operators in a couple of different ways. And we'll see some easy ways to do that, especially when we talk about fuzzing different controllers and fuzzing logic. But what if we turn on alarms when the alarm shouldn't be, right? That's probably the classic scenario. An alarm keeps going off when there's no reason for it. And then eventually the operators start ignoring the alarms. Well, what if one of the alarms goes off and yeah, you really did need to respond to it? And then we can also talk about, preventing automatic recovery. So having that true lasting impact in the environment. So that way, a controller isn't able to recover. And again, that's just going to leave the process that's running in the real world on its own, right? We have a runaway process at that point. There's no control. There's no monitoring and there's definitely no control. So we started to talk about, so as an attacker or a pen tester in a test environment, right? How can we change the operational mode of a PLC or other controller like SIS? Remember the safety instrument systems is just another type of controller essentially. And we'll go through some of these examples. So think what happens when I log into an engineering workstation. That engineering workstation is going to have not only the vendor specific software installed on it to access these different controllers, but it could also have information about accessing those controllers like IP addresses or credentials. Maybe those credentials are written or stored in a clear text file. Not that that would ever happen, right? Or what if maybe they're stored in some other type of application on the machine. Or a lot of these applications are now just becoming web interfaces, which means you're logging into them using a browser, which means people save their usernames and passwords in browsers, and browsers, right? They're not always known to be 100% secure when storing usernames and passwords. And even if they are today, right, there's going to be a vulnerability tomorrow or next week that's going to give you access. Yeah, now you have controllers, and we have one example that we're going to look at where the controller, the run mode, right, or the operational mode is dictated by a coil on the actual PLC. And we've already started to see how straightforward it can be, how easy it can be, right, to not only read those memories settings, right, those data points in memory, but making changes. What about how we can make changes through the HMI? Remember, the HMI is there for operators to be able to make changes in the environment. If an attacker can access the HMI, then the HMI is going to give them the ability to make those changes that an operator would also be able to. And we can also capture network traffic, right? We can capture commands like from the HMI to the PLC, and then we can replay those later at a time of our own choosing. Or maybe we can even make changes to the data before we resend it. So that's one option. And we'll start to see that kind of an attacker in the middle attack, or now what they call in-path attacks. I still like attacker in the middle better. And then program download. This is where, again, the OT world is different than the IT world. So when you usually say download, right, a program, it means you're putting it on your laptop, right? In this case, when we say program download, this means we're putting that firmware or that PLC logic on the controller. That's why I typically try not to say upload or download. I just say we're going to put, right, the logic or that new firmware on that controller. So how can we determine if a controller is in run mode? Again, we consider run mode the quote unquote more secure. It's not perfect, not a silver bullet, but it is more secure. So physically, right, if you're in front of the controller, right, you can see it might actually will have an indicator light typically to tell you if it's in run mode or which mode it's actually in, even if it doesn't have a key, a physical key switch or hardware switch, like a little dip switch. Or you can actually look to see, are there any activity lights? Right. So if there's no activity and you're sitting there watching the PLC, and at least for a minute or two, and you're not seeing anything, it's kind of like a network switch. If you're not seeing any blinking lights and there's no activity, it means it's not working. Right. So in that case, it probably isn't in run mode, or the lights are bad, but chances are, right, you're not going to be in run mode. Now you can also, if you have access to the vendor software, you can use that to then connect to the controller, and then that'll tell you what mode it's actually in. And then we mentioned there's a lot of controllers that will actually store essentially the operational run mode in a coil or potentially a register, right, to tell you what mode it's actually in. So here's a couple of common ways that we can remotely check, and we'll walk through these examples. So I mentioned with an unauthenticated protocol like Modbus, you could be able to connect to that controller, and if it stores its run mode as a data point, we could read that data point, that coil, that register to determine, right, whether it's in run mode or what mode it's actually in. Ethernet IP, there's actually, even in this case, you can see Nmap has a Nmap script that you can run to then determine whether it's in run mode or not. That was part of my master's thesis, right? Was to have this platform to be able to monitor all of your PLCs in the environment. So it would actually remotely monitor whether a PLC is in run mode or not. So that sample or that virtual PLC that we have, the simulated PLC, if you want, that we have for the class, it even has the ability, if you go to the PLC status tab, you can see, remember, it's programmed to be exactly like a Rockwell PLC. And it has the ability to change it from run mode to program mode or vice versa. And in this case, if I was to log in to that HMI, we can actually see, yeah, it actually says processor status program. So we know it's in program mode. So this is where, if we had access to, let's say, the HMI or the vendor software, we could connect to the controller, and then we would have that ability to switch between run or program mode in this case. Now, in LabShock, you have the ability to actually log in. So when you're in the LabShock environment, you have access to the PLC interface. In this case, Zachar Bernhardt, who had put LabShock together, used OpenPLC. So it's an open source virtual PLC that you can use. So you click on PLC or PLC service. It takes you to the login page for OpenPLC. And then, of course, there we just enter the default credentials of open PLC with the password of open PLC. Click login. And then boom, we're in. And it actually tells you on the first screen whether it's in run mode or not. So you can see here under dashboard, oh, there's the status right there. The status running. So we know in this case that the PLC, yeah, exactly. It's in run mode. And then you can see in the lower left-hand corner, we actually have the option, like I said, like when logging into a controller with the vendor software, you have the option, oh, right here, it's just click here to stop the PLC. Now, in this case, remember that the PLC drives the process, which in turn also drives the SCADA or the monitoring or the HMI interface that we have, right? Watching, it's monitoring, controlling the environment because remember, the HMI is pulling that data from the PLC, which in turn is pulling them essentially from the sensors that we have out in the field. So what happens when we just stop the PLC? So let's find out what happens. So we'll go back to the dashboard, right? We log in, right? We access the HMI interface. We click stop PLC. So once the PLC actually stops, and you can see it's in process, it says, okay, now the PLC stopped. Now we can go back to the HMI, and now we can see we have no visibility into the environment because the PLC, remember, yeah, it's dead in the water. And we can even see that there's that PLC connection error message in the lower right-hand side of the screen. So now we've lost our ability to monitor and control the environment because the PLC that allowed all of that to happen, essentially at this point, no longer exists. Now you also have to think though, well, what's actually happening out in the real world? Because the process was running. Remember, we had that pump running that was moving oil from those tanks out into right those pipes, like again, maybe to push through loading arms onto a tanker to be taken overseas. So that process could still actually be continuing. Right? That pump is still running. We just no longer have visibility, and we definitely don't have the ability to turn on or off that pump remotely, at least through the computers, right? Through the automation, through the operational technology. That's like any outage that could be caused by an incident, like we saw, like with the blackouts in the Ukraine. In that case, right, we lost our systems, and while we're trying to rebuild those and bring them up and running, right, we have to send people out into the field to manually monitor and control the process and the environment. So we can stop the PLC, right? That's where we lose the ability to monitor and control through the computer systems. But then we have to ask, and of course, every environment and every process is going to be different. But what's going to happen to that process when all of a sudden the PLC essentially just poof disappears? So keep that in the back of your mind. So in Lab 7.1, this is going to walk through a couple of different approaches, like with LabShock, but also using tools like Nmap to be able to remotely scan a PLC to determine, is it in run mode or not? And then look at, well, how can we make changes to the run mode, just like we saw with LabShock, where you can literally log into the PLC interface and click stop. And sure, that's a virtualized environment and you have it on your computer, but it's essentially how it also works out in the real world. So that's what we're going to be covering in Lab 7.1. Now, we can have a lot of API interfaces in the OT world, just like we see in IT. Of course, they seem to be everywhere in IT these days. And of course, we have IT and OT converging. And so we do see APIs that we can have that exist in OT that could give an attacker some form of control over a process. And so we can look at, and we'll actually go through a manufacturing example. But we do start to look at, and we do talk, I think, in the IT world a lot about API cybersecurity, but there's almost no talk in OT about security around APIs. But if you look at what those APIs are actually being used for, or what they could be used for, I'm going to start thinking, yeah, we really need to be having these conversations. Because what if an attacker can find an interface, and then they can use that to start making changes to a process? What if they were able to make changes to control or logic? What if they're able to read information from a different system or from a controller? What if they're actually able to send commands, let's say, to that controller to make changes out in the real world? That's what can happen. Again, that's why we need to be having these conversations. So here we have a food manufacturing process. So we have a mixing tank. We're going to bring in different ingredients to create a final product. Now, part of that process includes injecting liquid preservative into that mixing tank in specific volumes, right, at very specific times. Now, it's injected through that pump, and that pump is controlled by the PLC. I think that's kind of a generic manufacturing process that we could see. And you'll actually see what type of food that we're talking about, right? But we have, again, mixing tank, right? We're bringing in ingredients, and then we're bringing them all together, mixing them up to come up with a final product. Part of those ingredients is injecting liquid preservative at a specific time in the process, and a specific amount, and a specific time in which we're putting that in, right? Are we putting all of it in at one time, or are we kind of letting it trickle in, or somewhere in between? And all of this process, right, is controlled by that PLC. Now, what we'll actually also see is over time, right, we start to then look at, this is where we start talking about IT and OT worlds converging. Because in manufacturing, we've talked a little bit about it. Remember, in manufacturing environments, we have that manufacturing execution system. Sometimes sits on the IT network, sometimes sits in the IT, OT, DMZ, sometimes sits on the OT network. Just depends on how it's set up in the environment. Usually it's in IT, sometimes in the IT, OT, DMZ. And so it takes orders from, say, potentially the outside world, or at least the business, right? We'll enter that orders in some way, shape, or form into the manufacturing execution system. And then it's the responsibility to take that order and communicate it into the OT network to kick off the manufacturing process. So in this case, it does that by using a post command. Just like if we were sending or submitting data to a form on a web page. And you can see we're going to, in this case, post to that API gateway. And you can see we're going to go to that IP address, and on that IP address, there's an API that sits there at /API/v1/dosing/additive_pump. And if we know the right commands, right, there's a certain command that we're going to issue based off of the size of the batch, right? Then we know, right, to the commands to issue to get the recipe just right. Right? This is the whole part of, we're automating the process, including taking the order out from the real world through IT or through the business side, and then moving it through the MES into OT to kick off that process to manufacture the goods. And so then the API gateway accepts the request, and then it's responsible for submitting essentially that information or controlling, right, the PLC. So in this case, we talk about we can have a batch that we submit. We're going to give it a batch ID. You can see how much of the additive that we have to add, and then the flow rate, like how fast are we going to go ahead and inject or add this additive to the process. In this case, you can see, okay, out of the 150 liters that we have to inject, then we're going to let it inject or add it to the mixing tank at 50 liters per minute. So it's going to process is going to take 3 minutes overall. But this is the idea of how we can, use the API world, right, to help automate processes in OT. The problem is, like when we're bringing in other systems, if you want, from the IT world, right, we're bringing in all of those vulnerabilities. So now what happens if we have an attacker or a pen tester that wants to exploit this system? So one of the examples that we have set up in the course is where we have this salad dressing manufacturing facility. In this case, we're doing aged balsamic vinegar dosing. I'm a big balsamic vinegar guy. And so we actually have this interface and kept it really simple. So it's all text based, but then you can interact with it and then you can see the commands that you're actually submitting to then have it kick off that process in OT, right, for manufacturing. Now, again, this is one of those where we have to put on our evil thinking caps and determine how could we take advantage, right? Or how could we cause issues? How could we have an impact in the environment? Because what if I can go ahead and submit my own request? Once I know that command structure, what happens if I submit my own request to the API? And what does that trigger? And are there any security controls put in place to stop me? More than likely, there are no security controls put in place to stop you. And there's a lot of unprotected APIs in IT, let alone the vast majority of APIs that reside in OT or ICS or in the environment between IT and OT, right? That take data from IT and then move it into OT for the process. The vast majority of those are unprotected. Like, what could an attacker do with that? In this case, even just turning off the pump. And then at the end of the day, you end up with a bad batch of salad dressing that you have to essentially flush down the drain. And then you lost all of the money that you spent on those resources, right? On those different ingredients to actually make the salad dressing in the first place. So Lab 7.2 is going to walk you through that example using the text-based HMI. So it's really set up as a simple example of working with an API in OT. And I am not. So one of those techniques that we see a MITRE attack when it comes to execution, right, is graphical user interface. And you can start to imagine we've already started to work with different GUIs in the OT world, right? Especially HMIs, or what if you're on an engineering workstation, right, and have access, let's say, to that Windows desktop, to then have access to an HMI, or even, let's say, the manufacturer equipment for those PLCs, maybe those Siemens PLCs or those Rockwell PLCs, that you can then access that software and to then in turn access the PLC to then in turn issue those commands. Or what if you're uploading or you're putting new programming logic on the controller or new firmware? And so you can do those types of actions through different GUIs that are available. Now, especially when we usually are talking about HMIs when we talk about graphical user interface. So you think the HMI is designed, right, not only to show us what's going on in the environment with the process, but to allow the operator to make changes, right, to interact with the process, to make changes that might be necessary essentially in an emergency, right? Now the HMI should be programmed, should being the operative, key term, right? But the HMI should be programmed to only allow an operator to take actions that are, let's say, legitimate, right? That we would need to take action in the environment and shouldn't allow them to, let's say, even just make mistakes. Because operators at the end of the day, we're all humans and we could make a mistake and that could have catastrophic consequences in the environment. So we have to make sure that the HMI essentially is foolproof and that, yes, while it gives the ability to the operator to monitor, to see what's going on in the environment and to make changes, we're not going to allow them to make changes that are going to have some type of negative impact into the environment. So the HMI should be programmed to only allow legitimate commands to run, right? It's, we assume, kind of see here, right? They're pre-approved commands. They're like, it's a canned response essentially. It's like, click this button here, right? Remember our thermostat example, click this button here to make the temperature go up, or click this button here to make the temperature go down. But we should then also have things like, well, we can only have the temperature go up, let's say, to a maximum of 80 degrees. So we're only going to allow the operator to take actions that we would consider legitimate and not have a negative impact in the environment. And this does count as a form of living off the land, right? Because this is the HMI is a system, it's a tool that exists in the environment. And if an attacker can access it, and they're using the HMI to make those pre-approved canned changes in the environment, right? They're using those systems and those tools, the software that, it's part of the environment. It lives there. And so if you were monitoring for this type of activity, at least at first, it might not necessarily come across as something suspicious or malicious. It might not. Now, if you're looking for anomalies over time, they start making changes, something should jump out. But that goes back to, are you even monitoring the environment in the first place? Because most aren't. So they wouldn't know. So we can access the HMI, what if it's through an engineering workstation, or maybe the HMI is running Windows, so you can connect to it with remote desktop or VNC or TeamViewer, which we saw in the Oldsmar water treatment facility attack. So somebody had installed TeamViewer on the engineering workstation, made it accessible over the internet, and the attackers come in over the wire. Oops. But we can access the HMI in that case. And we can sit there and click and we can make changes to the environment. That's where we see a lot of hacktivist attacks these days, right? Once they get access to the environment, they just start clicking buttons, hoping that there's going to be an impact that they can brag about, even though they really didn't, take the time to understand the environment, right? They weren't trying to reverse engineer the process. They were just trying to have an immediate, quick, right, just impact. And then they could get online and maybe post a screenshot or put a video on Telegram or a screenshot on X, or it's just to brag, to kind of make their point. We hacked you, ha ha ha. But remember, the HMI is there to give the operators visibility into the process that's happening in the real world, and then to be able to make changes. So think, if an attacker gets into the environment, how exposed is that HMI? How exposed is the process? Or what happens if you do expose the HMI to the internet? Remember, you're not only exposing the HMI, you're exposing the process. and you're exposing control over the process to where an attacker or pen tester can have an impact. So here's an example, and you're going to see this in the labs, where as just kind of based off of this scenario, loosely based off of the Oldsmar scenario, where again they had that engineering workstation that was exposed to the internet over TeamViewer. An attacker logged in, accessed the HMI, and turned up the amount of chemicals that was injected into the water to make it safe to drink. But they turned up the volume to a point where if you would have drank the water, if the chemical had been injected, it would be deadly. So that's what you're going to actually work with. And you can see there's a little button on the right-hand side to simulate the attack. And this is where imagine if you were the operator sitting there. And this is, when it was explained that, the attackers, thankfully, when the attackers got in, the operator noticed immediately what happened. And so I'm imagining, alarms were going off. And so they were able to jump on it right away. I think that's the only way it would have happened. And so the systems did their job, right? There were alerts, maybe flashing screens to get the attention of the operator. We're going to talk through some scenarios and how we can circumvent that in the next video, and really the next two videos of the course, right? But that's what you're actually going to walk through in that lab. So when you think about, if I'm watching that water treatment facility, and then all of a sudden the attacker is able to reach into that water treatment facility because somebody installed TeamViewer on an engineering workstation, and then that attacker has access to the HMI to then make changes to the environment. So that's Lab 7.3. So we talk about modifying controller tasking. This is an interesting one. This is one that I have not had direct experience in working with, but it makes me think of kind of manipulating processes in memory on Windows systems. Because this is where we can essentially eject code into the system that it shouldn't necessarily be running by default, but we can trick essentially the operating system, or in this case, the firmware of the controller, to then run that code or that logic on the controller. And so one of the examples you can look at is with Siemens controllers and how Siemens uses organizational blocks, right? And there's I think of them as like these chunks of functionality that the controller uses. And I go back to my Windows days, and you're thinking of the kernel mode and user mode, right? We're separating the operating system versus the applications that run on top of the operating system. But these OBs, right, the organizational blocks, essentially add up or come together to allow the PLC to run through the PLC Scan Cycle. Remember the 4 steps, right? As we go through input, right, bringing in the data from the sensors, then running the logic on that data to then determine, do we have any changes in the environment that we need to make through outputs and then into housekeeping. And you can see, so Siemens has different, it's really fascinating when you start to dig in it. At least I thought it was really interesting. So they have these different blocks that will run or that'll trigger at specific times in the cycle, like when the cycle completes. So think of things like housekeeping, or even at the very end of housekeeping, or you can have them trigger at a specific time or time interval. Or what happens, and then think from a troubleshooting perspective, if a certain component loses communication. And so here are some of those organizational blocks you can see. So, and then OB1, OB100, right? Program cycle, right? Triggered upon completion of a program scan. Right? Again, at the very end, when we've gone through the entire PLC scan cycle. What happens when we bring a PLC online? and then it moves into run state. And then, so we have essentially at that point, it's like booting Windows, and now Windows is starting to load. Then you have to, in this case, start to initialize the logic of the PLC for it to actually do what it does. And then you can see a few, again, time of day, right? Cyclic interrupt, right? Where it's at a specific interval. So think of what, again, it's not only understanding how these work, but also start thinking about it from an attacker or pen tester perspective. Again, my mind automatically goes to, how this kind of works in the Windows attack or pen testing world. Going back to my days in Windows pen testing. But that's what actually happened with Stuxnet. And so you can actually really get into the details if you're interested to see how Stuxnet took advantage of these blocks and Siemens equipment to be able to run its code and also hide its code, to be able to stay as stealthy as possible in the environment to ultimately have an impact on those centrifuges to physically break them down over time. So it's really interesting and definitely can dig into a lot deeper. But again, that's where it really comes down to. It's really interesting. That's how I got kind of started going down this path into the Siemens world. I haven't worked a ton with Siemens directly. I've worked in Siemens environments and with their software and their platforms, but not with necessarily any of the equipment outside of a training environment, right? Directly. But this is how Stuxnet actually used different organizational blocks to do what it had done, right? To take essentially control over the controllers themselves and hide the fact that it was there. And then to start controlling the centrifuges to physically break them down over time while also hiding its presence from the operators. So it's really interesting. I thought it was interesting, and definitely maybe another more research project down the road. And so the last part of this section we want to talk about is lateral movement and how some of the common ways we can move from machine to machine. And we actually see these, you start to say, well, it almost looks like an IT cybersecurity course, right? So default, hard-coded, easy to guess credentials. Yeah. But and we can still see those in IT environments these days, but you will definitely see these in the vast majority of OT environments that are out there today. And so when you get, right, equipment, just like in the IT world, it's going to come with either default credentials that are the same on every single make and model of that equipment that anybody in the world will buy. Or you'll at least get, username and password like that the vendor will give you, maybe like the integrator will give you. But think there is equipment. Yeah, it comes with those default credentials. And so I know like my Click PLC, when you get a brand new Click PLC, it's like the default password to log in for anybody who buys a Click PLC is Click. I know, imagine that. But that means, what if, right, that environment, and you find that Click PLC online, right, they never change the default password. Well, quick Google search, if you didn't know what the default password is, will tell you, oh, it's Click. Try to log in with Click. Like, boom, you're in, because they didn't take the time to change the password. And I can understand a lot of times they don't want to, because that could cause operational issues down the road. What if somebody changes the password and then they forget the password? Or what if, that person, they win the lottery and they no longer work at, let's say, that factory? What if you have systems that have too many security features enabled? Think, well, what if, you forgot the password? Or what if, again, that person no longer works at the facility? So maybe you sit there and try to guess passwords, thinking, oh, maybe it could be this, maybe it could be that. And then what if they have safety features or controls in place to do things like, lock you out of the system? Or maybe, right, it stops the system from running. So that's why there's a lot of times, right, in OT, we don't enable those additional security features because they could cause operational issues or even safety issues down the road. So that's why you see a lot of default credentials and other quote unquote easy to exploit situations. There are some systems, and these are typically the older ones, where you can't actually change the default credentials. It is what it is. Good luck. Right. So we have to wrap compensating controls around it. But you can find those default credentials, right? Looking for vendor documentation, Google or AI it, right? Where you can chat GPT that, right? To look up, what is the default password for this Siemens S7 1200 PLC? There are some compile lists out there. I actually included them in the download directory for the course. So you'll find them, and actually included an example for the lab exercises. I think there's actually a couple of examples in there. So here's some links to a few of them out there. There's not a lot. I tried to compile them and give everybody credit into like one location and put that in the course materials to download. Now, hard-coded credentials are those that are in a system that cannot be changed. That's the whole term, hard-coded. And a lot of times these ended up like developers would put these in because it's one of those, it's kind of security through obscurity, right? Which does not exist. But a developer, puts in this hard-coded credential so that they know, oh, if I put in the password, I don't know, I love pizza, that all like, and maybe there's a certain, maybe a listening port that you would have to enter it in. It would give you full, complete control over the system, right? The developer put that backdoor in to make it really super simple for them to log in. And maybe they were just meaning to do it during development of the asset, but then they forgot to take the backdoor out, right? Or they just left it in there on purpose, thinking, well, an attacker's not going to find that. But attackers will find it one way or the other. And so you can find them by inspecting like the actual code, the firmware itself. And you can use different tools like Binwalk to go through a piece of firmware to see if there's something like hard-coded credentials that are included. And again, they're written into the firmware. It's not like a default credential that you're able to log in and change. No, the password is there and it does not change. The only way to fix that issue is to fix it in the firmware and then to download that firmware onto your system and then put it on that controller. Of course, there's also easy to guess credentials. Because remember, most systems either require a username and password or just a password to access. And you see this even more in OT for sure. A lot of systems just want a password. And so again, it goes back to a lot of environments, right? They don't want to have issues where all of a sudden an operator goes to log in and they mistype a password because it's 30 characters long. They don't want to have those issues, especially if they're trying to respond to an urgent situation. So a lot of OT environment, right? If there's a default password, leave it default because everybody knows what it is, right? That's right. It's kind of the convenience factor. But if it's convenient for operators and our users, then it's all right. It's going to be very convenient also for attackers. So there's a balance in OT, right? It's a very different discussion than in IT. It's a very interesting balance. between, how secure do we want passwords or not, right? We don't want them so secure that it prevents an operator from doing their job, especially in an emergency situation. So in the lab, there's actually a SCADA interface. So when I was putting this together, I was thinking of the 2022 attack by Sandworm and creating the blackout in Ukraine, and where Sandworm had gained access to the OT network of the power company. Right? And we're able to find the SCADA admin interface and log in with easy to guess credentials. And then once they were inside the interface, they turned off the breakers, which created the blackout, and then they wiped all the machines. So you didn't even have a Windows machine to log in to that web interface, because the web interface and that system no longer existed. But that's an example. And there's a couple of different ways to interact with that system in the lab and run a couple of password attacks. So that's what you're going to see in that final lab. And that's it for this video. So I appreciate you for being here, and I will see you in the next video.